Yeah. My name is Kunal Chand. I recently graduated with my PhD sometime last year, I think. My specialty is building computational toolkits to help researchers analyze vast amounts of image datasets and finding patterns in them. My co-presenter is Hayden. She is a researcher at the Centre of Digital Cultures and Societies at the University of Queensland. QT stands on the lands of the Turrbal and Yugara people in Mianjin, Brisbane. I like to pay my respects to elders and leaders past, present and emerging. We pay our respects to customs and custodians of the lands and waters on which QT now stands, and recognise that these lands have always been centres of learning and teaching. So, images already on each desk?
Almost. We're going to get there.
So rather than giving you a standard presentation and saying this should be this should happen, this is what we do, we're just going to give you the problem and just throw it straight at your face.
All right.
So, you want to take over?
Sure. Okay. So we've given you a stack of images. These images, Kunal has collated from Instagram many years ago at this point.
Oh, actually, this was
2 years ago?
This was actually one of our software engineers on this program.
Oh, okay.
She collated these images as part of a research project. We're going to run an exercise with you and see how you compare to what a computational method can compare to.
Okay, so what we would like you to do is just take a look at your images. Let's spend the next 15 minutes sorting them into groups. Sort your images into groups. Any groups you like. No more instruction other than that, I think.
Yeah. Organize them however you want to.
Yeah.
All right. So despite all of us being humans and having almost similar images for the most part, we have come up with very different methods for categorizing them, for structuring them. So what happens when we throw a computer at it? So background for this project, and actually history of this project, my PhD was focused on the issue of how do we build computational methods that can analyze visual data sets? How can we find patterns? How can we group these data sets to find new patterns? So visual media is becoming increasingly prevalent online. If we think about the first types of social media, they were mainly text, and it still are, but with the advent of Instagram and YouTube, it's starting to move more into the visual realm, if it already hasn't become the prevalent one. The issue is most of our methods are currently focused on text. How many of you are natural language processing or perhaps topic modeling people? Yep, 1, 2, 3, 4, 5, pretty much half the room. Okay, so with that in mind, with the prevalence of visual media in mind and the lack of visual media methods in mind, we need such methods. And these methods need to operate at scale. So we're not just talking 10, 20, or how many do we give them? 200?
Yeah, something
around
like
200 images. We're talking about Instagram scales. We're talking about 50,000 images, 100,000 images, millions of images. These are the levels Instagram communities operate at. So how do we tackle this issue? First, we need some help from another field. In this case, computer science. Computer science has a field within it called computer vision, and the computer vision field is focused on enabling computers to operate on images, to understand, detect, and perform other actions on visual data. In this case, for the technical specifications, there's a model called VGG16, pre-trained on ImageNet. The model and the dataset it's pre-trained on are very well known in computer science. They are pretty much the gold standard of its time. Not the current time, but of its time, they were the gold standards. And the technology is called convolutional neural networks. It's a type of machine learning that specializes in operating on visual data. So, how many of you know what machine learning is? Most of you? Yep. So this should be pretty quick to flow through. You have an input layer, hidden layers, and output layer. Input layer is whatever your data passing in. Hidden layers are essentially the core of the machine learning model. You don't know what they are, what it represents, how it calculates. Well, you do know how it calculates, but you don't know the exact values of it at any one time. And then you have the output layer, which is what you want it to produce. So for image classification, I could give it an image of a flower, pass it through into the model, and it outputs flower. Object classification. The thing is, if I was to truncate that final layer, remove that output layer, instead of flower, I could get the exact final values of those hidden layers. The thing with this is these values represent how the model would essentially represent the image in its embedding space. So 4096 values to represent an image by the model. So this is what we call an embedding vector. So now the pipeline is I pass an image in and I get values out. Now, for the sake of simplicity, instead of 4096 values, I'm just going to output 2 because I'm not going to draw 4096 dimension graph. So with 2 values, you can draw a single point on a Cartesian plane, XY axis, XY coordinates. I could pass in another image, and with the workflow, another set of coordinates, different place. Pretty simple so far. But what happens when I want to compare them? Now, this was the challenge I gave all of you. How do you compare images? Well, computers can do it quite simply with this, because now they have numbers, and computers are great with numbers. In this case, Euclidean distance, but you can have other metrics. In this case, we're just going to simplify it. A squared plus B squared equals C squared. So C equals square root of B squared minus A plus A squared. What happens when I give you a lot more images? What can you do with this? I could definitely get a lot of points on that, yes. On the graph, yes. But how would you organize this? Now you see the similarity between the challenge I gave you and the challenge here. Well, I'd pass all of those points, get their vectors, get their XY coordinates, and then plot them. But now you'll start to see there's a certain pattern emerging. Now, I've mentioned that you'd have 4096 values, but we're going to use 2 for the sake of this. You don't always have to use 4096 values. In fact, it can be detrimental to use that many values. First of all, you are trying to calculate 4096 values per image. And if you have 100,000 images, that's 4096 times 100,000 images. So there is a method called principal component analysis. It is essentially a way of reducing the number of dimensions or the amount of information required to represent a piece of data. In this case, I'm reducing it from 4096 down to just 10 values. Now, still going to stick with the same analogy. I've still got points on a 2D plane, but instead of 4096 per image, it's just 10. Now, grouping is something I can do. And computer science offers us something called clustering algorithms. Essentially, given the distance from each other, how well can you form groups? In this case, if I was to go back one, it's pretty distinct groups, 3 easy groups to form. And then we'll have to recognize they are separate groups. In this case, we call them clusters. Now, when I apply them back to the images, I get those clusters, visual clusters. How many of you were trying to cluster based on what the images contained, where they focused on, or perhaps what they represented? Yep. Would you agree this is doing a similar thing? Yep. It didn't use any words whatsoever. No words, no text, NLP, go away. So, sorry? Oh. So remember how I said an image model, you can pass in an image, you pass it through the model, and you get a text output. When I modify that output, and I remove the output layer, I instead get numbers. Yes. Yep.
What she want to ask is like how computer can read the photo like us, and I guess we should mention that we are the one who actually do this stuff every day, right? The capture. That's how we have big company.
Sorry, Kunal, is this representing like pixels on the image? Is the image broken down into like squares and then somehow encoded?
Oh, yes and no. So when it's passed through the model, every single pixel is read by the model. But but the model processes it as a group of pixels. And what it does is, based on certain groupings and what it has already trained on in another data set, it starts to recognize, okay, this might look like something similar to this. And then this image could look something similar to another object it's been trained on. And so based on those, the values change based on similarity.
Sorry. But I mean, like, correct me if I'm wrong. Even before that, basically how the model learned this is basically we get a bunch photo of flower, and they actually learn the pixel.
Oh yes.
Before that, right? So
when I was talking about, there you go. So yeah. Keyword here is pre-trained. Yeah. So it's a model that's already been trained on images. Yeah. So the data set is called ImageNet. It is a very well-known data set in computer science, and convolutional neural networks were one of the big breakthroughs in terms of visual processing, in terms of processing images. Any further questions on that?
Is that a labeled data set or unlabeled data set?
Labeled.
Labeled.
Yep. It has to be labeled if it can.
Of course, yes, makes sense.
Text, yep.
Flower is the label.
Yes. All right. Okay. So now we've got clusters, but what happens when we have thousands of images? Is it still just going to be 3 clusters? Yes? Really? Really? I mean, it could be, but it's unlikely that there are just going to be 3 patterns amongst 1,000 images on Instagram or perhaps videos on YouTube. So we need to prepare for many patterns, and then we need to be able to store this because as researchers, we need to be able to retrieve these analysis results. We need to be able to visualize them. So how many of you know what tree data structures are? Yes? Yes? Yep. Anyone who doesn't know? No? 1, 2, 3? Okay. So quickly a tree data structure is a well-known data structure in computer science. It's great for handling hierarchical relationships. So there are 3 main parts to a tree data structure. There is the root. Each of these points are called nodes. And then there are 3 different types of nodes. The first at the top is called the root. This is essentially the highest level in that hierarchy. In terms of our image data set, this point will represent the collection of all of our images. Next, underneath that are nodes. You can have as many nodes as you want, as many depth as you want, but each of these will represent groups or clusters. So you have your whole data set, and then when you cluster it, each of those clusters become a node. Now, after that, there's a special kind of node that is at the lowest level of the hierarchy. That is, there are no nodes connected to that. It has no more children. These are called leaves. So root only has children. Nodes have parents and children. Leaves are children, but only have parents. They don't have any further children of their own. Any questions? No? Okay. So what happens when we apply everything we've just done onto an image, onto a, let's say, large-scale image data set? In this case, alcohol advertising is the project we're going to be talking about for today. Can you take over?
Sure. All right.
You've already got one.
Yes, I need I'll use the clicker. Okay. So thanks, Kunal, for the very technical description. Hopefully we can walk through this example together and it will start to make some sense on how you might actually think about applying this in your work. So this actually came out of some of my own PhD research, where we were interested in how alcohol companies were targeting Facebook users in Australia. And we amassed through the Australian Ad Observatory project, you've probably heard a little bit about this project so far this week. We amassed a corpus of advertising images by asking Facebook users in Australia to donate them to us. And this was in the first phase of the Ad Observatory. So this morning, Dan Angus and Dan Tran presented about the mobile app that they trained to collect advertising. That was like sort of the version 2 of the Ad Observatory. This is version 1. And in version 1, we had a browser plugin that research participants could install on Chrome or Firefox, and it would computationally snip out their advertising as they scrolled their Facebook feed in the browser. And it does that rather than using screen capture like the mobile app. It actually is able to use the tags that are in the browser to identify what's an ad and what's just a organic post on Facebook. So we ran that project for about a year. We had, as you can see here, almost 2,000 people across Australia donating their ads to us. And we collected over 200,000 unique ads in the study. And that included about 8,151 alcohol ads. And so my question was really about how, who sees what ad? If we sort of start to collect different ads that look like this, and some of them tend to look more like this, new catalog out now, buy this beer, buy this wine. Oh, there's an even better example, versus some ads, start to look a little bit different. They are people, they are beautiful scenery, they're sort of people on a camping trip having a beer around a campfire. So I was interested, who was seeing those ads, and then who was seeing the ad that said, buy now, it's on sale? And when we start to think about this kind of advertising that we see on Facebook, it's not just each individual ad, but really it's sort of about when you're scrolling, you are taking a sort of path through all of the ads that are available on Facebook. So, one person, I've got out of order here. Here we go. We'll go ahead. One person might see this ad, and then that ad, and then that one, and then that one, and then that one, and then that one. And someone else might take a totally different path through the ad space, and so on and so forth. And this is a completely unique experience to us all. So when we're thinking about advertising on social media platforms, it's not just about this one individual image, right? Just as you were sorting images here, it's not just about one image, but it's about the collection of images and what they kind of come to represent in our saturated media environment, right? We're bombarded with these images all the time. And some colleagues of ours have really, leaned into the kind of colloquial term of the vibe. Everyone's feed has a kind of vibe that's constructed by the images that they see. So each person has their own vibe and their own kind of path through the advertising space. So with so many ads and so many images, how can you actually start to make sense of what people are seeing and when, and what ads they are targeted with? So what we did was we selected 12 participants out of our 2,000 because we were interested in alcohol advertising. We selected 12 people who saw the highest proportion of alcohol ads relative to all other ads they saw. And we used Kunal's work called the image machine, which is his image classification model. Clustering. Okay, I always get the two confused. See, I'm not a tech person, I'm sorry. And this is a screenshot from the cloud version of the image machine, which is available for people to use. I think if you get in contact with Dan Angus at QT, he can help you get started with this process. But essentially what we did was for each of our 12 people, right? So the first person, we took their collection of ads that they donated to us. So we isolated their collection of ads out from the entire set and put it as its own mini subset, its own collection, into the image machine. And the image machine went ahead and classified these images based on different qualities that it identified. Clusters the images. But if we drill into alcohol advertising in particular, you can see straight away that, I guess I should go back a step to your tree map. Or no, you don't have to go back in the slides, but this is what Kunal was talking about with the tree. And when the image machine clusters the images, it breaks them automatically into 16 different clusters using a k-means clustering algorithm. And so what you see here when you first log in right at the top, this is the very highest level of those clusters. Each of these numbers in the pink represents how many images are allocated into that cluster. So even though they clusters may have similarities, but it takes the top, sorts them into the top group.
Okay, so every time it clusters, it forms a cluster. Each of those images you see represents a cluster. That particular image is the averaging of the cluster. What is the average of the XY coordinates in that domain, in that cluster? That's what you're seeing with those images. So it's an average representation of what you'll expect to find in those clusters.
Any questions so far? You look skeptical, Mike. Yes?
No, slightly different. Yeah.
Okay, I'll keep going, but please, bring your questions. So, because I was interested in alcohol, you can see straight away that there's two kind of clusters right at the top that are alcohol ads. This one, which is box wine, and that one, which is a bottle of whiskey. And we can see there's 345 more images in this group and 214 in that group. So when you click into, yes? Well, it's an excellent question. Yeah, well, no. So if you click into it, you might see, yes, a lot of things that look like boxes. Like you might see a lot of other images that share this kind of, there's some boxy shape in the middle. You might see other images that have a white background with some kind of border. It could be a variety of qualities.
So essentially, every time you cluster an image, the grouping are visually similar images. We won't always know the characteristics, but usually at these kind of specificities, we can guarantee there are definitely going to be box-shaped things there, or wine or whiskey bottle-shaped things in the other one. That's what we can say.
And I guess I should add that for this participant, so I said this is one person's ads that they donated to the project. That was almost 5,000. So that total image count that you can see at the top. So that was just one person alone, what they donated into the project. So we are talking about quite a substantial corpus of advertising. But let's say you were to click on this whiskey ad. Underneath, it looked like this when I clicked on it. And we can anyone see the sort of pattern that might start to emerge here? Price, title, background, a bottle, right? Liquorland, some numbers. It's like bottle with numbers. And so then putting my HASS researcher hat back on, this is what's often called direct response advertising. So direct response advertising is the advertising that you see that's like, this is $15, buy it now. Click here, buy now, add to cart. That's called direct response advertising. And we can see, for example, that this participant saw quite a lot of direct response advertising out of all the alcohol advertising that they donated to the project. On the other hand, there's also those other sorts of advertising that I mentioned, the beautiful people on the beach, having an Aperol spritz, having a great time. And that might look something more like these clusters. So this is a different participant. We similarly put his images, and this was one grouping. We can sort of see a pattern here, colorful cans of beer, of premix, that kind of thing. And then this darker kind of moody, vibey cluster, these 3 ads are alcohol ads at the top. And then these 4 are for other industries and other types of products. And so I think that's really interesting because that's where we're starting to see that brand advertising. Brand advertising is the beautiful people on the beach, right? Brand advertising is maybe people have actually seen this ad. It's like, Dan Murphy was a guy that worked at the docks and he imported alcohol to Australia and he opened the world's first liquor store. Anyway, that's the gist of the ad. So it's not telling you what does Dan Murphy sell. It's not telling you how much does it cost. It doesn't tell you where is a Dan Murphy's or, what does this product taste like, but it's really trying to build that kind of effective connection with the brand. So we can see how that first participant was really seeing that type of alcohol advertising that was very much like a cost and a price and a product, whereas this person was seeing advertising that's more about the sort of visual aesthetic of these products, the emotion associated with the advertiser. So it's a very different kind of persuasive appeal that's unfolding in their Facebook feed. And so really where this kind of nets out in terms of implications for alcohol advertising in particular is that we can use this method to think about how some users are seeing much more direct response advertising, while others are seeing that brand advertising, and that we don't see those types of advertising equally or interchangeably. And that's important because, we know with sort of algorithmic advertising models where people are targeted, right? They're retargeted. You look at a pair of shoes online and then that's the ads you see, right? Everywhere all around the internet. And so this is really problematic for harmful products like like alcohol, like gambling, right? Products that can cause harm to people. So people who are at risk of using alcohol and at risk of harm from alcohol, we know that they are more likely to be disproportionately targeted with alcohol ads. But by using this visual method, they're not only more likely to be targeted by alcohol ads, they might also be more likely to be targeted with ads that are direct response. So someone who purchases more alcohol might not just see more alcohol advertising, but they actually might see more advertising that's urging them to engage with alcohol products. And more broadly, you can kind of think about this, how social media platforms use advertising to sort of activate consumers in particular ways. We know from other research that platforms like Instagram and Facebook are very good at connecting into a emotional moment of their users, right? They know when you're feeling a little bit sad or, a little bit insecure. There's a breadth of research that focuses on that. And so when we connect that again back to advertising and the sort of actions that we're urging people to take, we can think about how that visually appears in their feed as in the ads that they see. That was my example. I hope that was legible.
Before we conclude, I'm going to show you some examples of how the image machine has evolved since then. So how do I change this? Share.
Is there any questions in the meantime? Yes. Oh, yeah, there you go.
Do you know what's the individual difference for the people who see the direct advertisement compared to the I'm selling you an identity branding?
Right.
Have you guys looked at that?
Like quantitatively
have you guys
see of how much one occurs versus
that, and why, like the persona of the person who are, so for example, is it someone who's just like, looked at Dan Murphy once, or is there something that, more of personality. I don't know personality just because background is like, but yeah, I don't know.
No, it's a really interesting question. So thanks for that. In this study, I did not go to the length of like quantitatively saying, you know, this person saw 100 direct response and they saw 100 of this. So we haven't gone to that length, but rather using the visual method to kind of get an indicative sense of how that might play out unevenly. But I think it'd be really interesting to do that.
I can't get it otherwise.
And then I guess in terms of personality, some of our colleagues have thought about it in terms of like a vibe, right? And so not just looking at one, I only looked at one product category of alcohol, but you can really start to see for some participants how alcohol fits into their other interests and other interest categories. So, you know, there's like one, maybe you've seen the ads for, there's something called Good Pair Days, which is like a wine subscription. They deliver it to your house. It comes in like a pink esky. It's very Instagrammable. So, you know, those ads are always coming alongside other ads for Lululemon, like skincare products, you know. Yes, exactly. The Aperol is another really powerful visual, like so iconic that we see how it really fits into, like, you know, sometimes the Italian piazza, or sometimes it's in a club with a DJ. So you certainly can start to see those more like qualitative kind of patterns coming.
I don't know, like gender or like age and things like that.
Yeah, absolutely. Okay, Kunal's got this working. Great.
All right, any questions before that? Or before I move on? All right, so this is the latest image machine. It's not on the cloud. It's something I developed locally because trying to get it work on the cloud is going to be a nightmare every single time. So this image dataset of the alcohol, this one has 32,000 images. So now we're talking about scaling it up, scaling our operations up. If I was to group all of this up, it splits it into just two clusters, because at the immediate level, it'll only see two main patterns. The computer will only see two patterns. One with bottles and glasses. And if I was to see the other patterns underneath this, I can see, oh, more bottles, and then more bottles. I could also go into this one again. And let's see what's in here. Oh, cans and a bottle. I could keep going, but if I was, let's just go one more. Anyone want to guess what the patterns will be here? Bottles? Bottles? Oh, look. It's not necessarily a bottle. This one's kind of a bottle, and this one's got a can there. Now, what happens when I want to see all of the images? Well, you see, this one has duplicates because multiple people saw the exact same ad. But in collecting some of these ads, some of these were actually MP4 or GIFs. So we accidentally collected every single frame of those. So we might have that as well. But you can see for the most part, there are definitely visual patterns, especially this one that keeps continuously appearing. But we can see there's hands, glasses, hands, glass, just the glass. Then this one stands out, but then it's still got bottle there, still got a glass there. So this is just one of the clusters in our image dataset. And you can see we had to go quite deep into the tree structure. So root is the top one. It's got all the images. I then went to the 0th cluster, then the first cluster of that, first subcluster of that, then the 0th subcluster of that again. And that's where I get still 4,000 images, which is still huge. If I was to go back to the top here, and let's go through the other route. What do you think we'll see in this one? What do you think the patterns will be if I was to go into this one? Fruit, maybe? Cucumbers? Cucumbers specifically? Okay, let's see. Suddenly, there's not really fruit anymore, is there? Color? Colors, okay, could be colors. Could be. Which one should I go through? The first one or the second one? Second, okay. What do you think is going to show up in this one? Letters? People? Neither. Remember, the one before, this cluster still has 11,000 images, and I'm only showing one image out of 11,000 plus images in the same cluster. That image is just the average. It's sort of the center of the cluster. It might not be near any of the other images, but it is the average or the center of the visual patterns. Now, another thing to note is the further we go into a tree, so the deeper we go, the more apparent the visual patterns become. Because there are less images per cluster, it's easier to see what the patterns become. So, which one should I go through now? First or second? First, what do you expect to see here? Text, okay. So there's 5,000 of them. Oh, there's some text, but there's also fireworks and whatever that is. Could be a color. Yep.
When we say it's representative, do we mean that it's the mean in like the graphical space, or do we mean it's the mode as in it's the most frequent type of image?
It's the mean.
I'm assuming that, right, so that's why we're seeing like imagery of text and then like things that only vaguely like look like the thing.
Yes.
Thank you.
Did anyone else notice a pattern for these three? Or in the previous one? So celebrations. But do you think computer models, or rather a computer model from over 10 years ago, maybe 15 years ago, would be able to associate this with celebrations? Probably not. Could be a contrast thing. There's also a funny one. Go one back. What do you notice about the aspect ratio?
It's the
Advertising isn't just on phones, it can also be on laptops. Phones are known for portrait orientation advertising. So when I went to the left, that's portrait. That's almost certainly a mobile phone ad. And then its sub ones, the subclusters, are also all portrait. So suddenly aspect ratio plays a part in here. Now, if I was to go in through this middle one, what would you expect to see? Text? Portrait? Okay, portrait, yes. Perhaps. No, it's no longer just portrait, but there's definitely text. But most of them are portrait, which is why it belongs here. Oh, yes. So when the model groups something, when it clusters it, it's not just one aspect. It can be multiple patterns. So when there are multiple patterns, we need to still be able to break those patterns into further sub-patterns. And so if I was to go back to, oh, please, teams, don't fail me now. Oh, please don't fail me now. Come on, come on, come on. 3, 2, 1. You can, okay, close enough. It works, which is more than I can say for what normally happens. So, if you remember this data structure, the tree data structure, I said each of these nodes are a cluster. But then if each cluster is essentially a grouping of visually similar images, they're a grouping of visual patterns. And I've told you they can be patterns within patterns. So now you see why hierarchy is very important, because they can be patterns within patterns within patterns, and the tree data structure efficiently represents that. Now, one weakness of this particular method is that, oh boy, here we go again. Allow, please work, please work. Yes, okay. The issue is whenever I go into just one of these clusters, I can only see what's in that cluster. I can see images relative to each other within that cluster, but I can't see it relative to the rest of the data set. So I can't see what this particular image or any image in here would relate to something in this cluster over here. Or perhaps, let's just go, I don't know, 0, 0, 0, search. Okay, 80 images. Like this one here. So how do I overcome this limitation? Because it is a limitation of the image machine. That's where a second method comes in. This bloody thing. Okay, stop sharing and then share, but I want to share a particular one. Share this window, but that. So this is a different representation, different way of grouping images, but actually it's very similar to what we've done before. So you remember how I said whenever I pass an image through a model, I'd usually get 4096 vectors and I'd shrink it down to just 10. What if I was to change the model and I was shrinking it down to just 2 dimensions, an X and Y coordinate? Suddenly I can plot these images according to their X and Y coordinates, and I can just overlay the image on top of them. So that's what this second method is. It's called UMAP. In this case, I'm using something called CLIP, Contrastive Learning Interpretive something. I forgot what it is. It's a model that allows you to operate on both images and text. In this case, I'm only using the image aspect of it. And if I was to just hover over any one of these, I could see, ideally, a high resolution image of it, but Teams does do a lot of compression. Thing is, I can just hover over any of these. I can see the pattern. That's a lot of bottles or landscape. This one over here, there's definitely a dark green over here. This one is, it's a certain visual pattern. The thing is, these visual patterns are no longer isolated to just their cluster. I can see each image and each pattern relative to the whole data set. That's the power of this. I can take this even further. I can also zoom in. So there's this island over here. We can see general structures start to form. There's a little island over here. I like using geography because it's much easier to explain with. So if I was to zoom into this, suddenly, oh, look at that. All of these text-heavy images come in. Advertising around these companies on the text basis. Now, the project itself, the alcohol advertising project, we decided to group these advertising entities into three different groups. There was producers, venues, and distributors. We found that, for the most part, this was venues. Venues use this kind of advertising, this visual pattern, to advertise where they are. Now, if I was to reset, what do you think this top green one here is? Any idea? Text? Actually, it's a very specific kind of green. That should give you a hint. Let's zoom in. Yep, it's Uber Eats. Has to zoom in there. Oh, okay. Okay. That particular kind of green, particular pattern of advertising, we can isolate to a certain company. Up here? That just happens to be a very portraity one. Which side? This one here? Now, so why is this one placed over here? What's the nearest one to it? Perhaps this one over here? Perhaps over here? So it's kind of similar to this island over here, but it's quite different in its own right. Yeah. Okay. Now, this is pretty cool, and it's definitely a lot of fun to look at. What if I told you any of you, if I gave you this exact file, it's just a HTML file. In fact, right here, it's just a HTML file. So all those actions of zooming, analyzing, all of that, I could just copy paste this HTML file to your computers. You could do the exact same thing. You don't need the code. You don't need any of that. But it becomes more interesting when, let's say we're doing a paper on something and we want to see just what are the general patterns. So we can see here in this area here, it's groups of people. If we go down here, it's more venues, single people or groups of people, DJs, black and white here. It's groups of people still. But then if I was to go off onto this side over here, suddenly it's more architecture, venues. If I was to go towards the center again, center of this giant body, suddenly focusing on drinks. If I was to go up to this image, this group over here, it's food and drinks. So now we can start to see patterns within the data set at a higher level. Final thing, when you see these patterns, and let's say you want to do a paper on them, please, for the love of God, work. Okay. You can actually get pretty cool visualizations like this. In this case, I get to draw the patterns, and I just isolated some images from the grouping. So for the green group, I took one from each corner because it looks roughly like a rectangle, if a bit weird. Bottom left, top right, bottom right. That's how I grouped them, and that's how I drew the images out. I get the general outlines of it. Orange ones, orange group. We saw a text advertising. Similar thing here. For the red one, there was a group about architecture. I highlighted it there. Gray, or black in this case, food and drinks. And blue was mainly, well, just advertising of the product, the bottles themselves. So 2D UMAP allows us to see patterns relative to the whole dataset, images relative to the rest of the dataset. So what does this allow us to do? It allows us to see patterns within large-scale visual datasets. What do those patterns allow us to do? Well, we can talk about them. We can investigate them. We can explain or perhaps research. Why do these patterns exist? Why do advertisers use these patterns? And this is just an example of alcohol advertising. What if it's another visual dataset? What if it's something like Instagram communities, like the one we had you do? The dataset you had, or the postcards, photo cards, whatever they're called, those are something called the cores dataset. If you've heard of cottage core, alt core, void core, those are what those communities are. So online communities probably have their own visual patterns, especially on Instagram and YouTube. We now have a method to analyze this entire platform, the entire community, based on their media. That's what Image Machine and UMAP allow you to do. I think that was pretty much it for the slides. Stop sharing. Go back to the slides. Come on, teams. Final run. Almost there. Oh, come on. You can't even load the previews of the slides. What's it doing? Okay, so key points. Visual media, as I've said, is becoming more prevalent online. Computer science allows us methodologies and tools, capabilities to analyze this visual media. There is a need for exploring how these computational methods from computer science enable more capability for researchers in this field.